Hello, let's get started. Good morning in Pittsburgh and good night in Beijing. Hello, everyone. Welcome to the inaugural Raj Reddy lecture in artificial intelligence and the celebration of Raj's 50+ years at the Carnegie Mellon University. We are so glad you could join us today. We have over 2,000 people registered for this event from all over the world. My name is Harry Shum. I'm one of Raj's students. I'm currently in Microsoft Research Asia's office in Beijing, China. So I know you are all here because of Raj, and Raj needs no introduction. But I do want to tell you a little bit my special relationship with Raj. I was his student at CMU from 91 to 96. And today I'm going to share a little secret that I learned from Raj as a first-year graduate student. So when I became Raj's student, I asked Raj, how should I allocate my time? And Raj said, look, you have 168 hours a week. I suggest you to use 40 hours for your coursework, which I did pick 5 classes the first year. And he said, then you use 40 hours for your research work. So that's 80 hours. So that's a good lesson for the first year hardworking graduate students. And Raj, of course, is a father figure to so many of us. And he's very demanding as an advisor. And he's just like a caring father and always watches out for us and promoting us relentlessly. We love Raj. So then you say, why we have this Raj Reddy lecture series today. We all wanted to thank Raj and honor Raj on a permanent basis. One way to do that is a recurring event that provides some public recognition and getting people together. Well, this time we do this virtually because of COVID. This series will feature leaders in AI technology and research. Today, we are very happy to have 3 Turing Award winners, Hinton, Yoshua Bengio, and Yann LeCun, joining us today to kick off this series. Of course, I'm not the only one for whom Raj has been a major influence in work and in life. Next, we are going to hear a pre-recorded message from another student of Raj, Dr. Kai-Fu Lee. Please roll the video.
Hi, this is Kai-Fu Lee. I'm a student of Raj Reddy. I'm happy to say a few words before this first Raj Reddy AI lecture. I went to CMU in 1983 and chose to work with Raj as my PhD advisor. And he's been wonderful and full of wisdom and gave me a lot of great ideas. Probably the most memorable moment of my PhD was when I wanted to try something different, different from what he wanted me to do. I wanted to try to use statistically based machine learning for speech recognition. And when I told him about that, he thought about it and then told me that he really wasn't sure and didn't totally agree with my idea, but he said, Kai-Fu, I will support you. I was really surprised with this feedback. But what he ended up doing was much more than verbally support me, but provided me with 30 workstations on which I could run my experiments. And my work ended up being quite successful and part of the first working speech recognition system under DARPA. What he said to me that moment, I think something I treasure for the rest of my life, because knowing that in scientific endeavors, there is no right or wrong. Everybody's an equal, and we should support others with our full heart. And that is a way of scientific pursuit, and it's also a way of management. So that's why in my book, AI Superpowers, I dedicated to Raj, whom I called my mentor in AI and life. Thank you, Raj.
Thank you very much, Kai-Fu, for this wonderful message and heartfelt. I'd also like to mention that today we are launching a fund in Raj's honor, another way to honor Raj permanently by making sure that those who follow in his footsteps have the resources they need. A handful of lead donors have already stepped up and raised about $1.5 million. If you would like to join this effort, we'll be sending information out. We'll be sending this information out about the fund after the event, when we also send you the recording of today's session. Just a quick housekeeping note before I introduce Professor Martial Hebert, Dean of School of Computer Science. There will be a live audience Q&A with the 3 Turing Award winners and Raj at the end of the lectures. We received many excellent pre-submitted questions, and we will be accepting more live questions as well. So please feel free to ask your questions via the Q&A box at the bottom of your screen. So next up, we are going to hear from the Dean of Carnegie Mellon's School of Computer Science, Professor Martial Hebert. Martial has been the dean for about a year, but he also has been in Carnegie Mellon since 1984 in the Robotics Institute, which of course Raj founded. So Martial, please.
Thank you, Harry, for kicking off the event. Let me just spend 1 minute placing this event in perspective. Today, we are introducing a new lecture series intended to highlight transformative progress in AI. Naming it after Raj is only fitting, as he has himself transformed the field of AI through its research and scholarship, which earned him the Turing Award together with Hinton. Closer to home, of course, he has built so much of what is now the School of Computer Science. For example, the vision of the Robotics Institute 40 years ago. But far beyond, globally, he contributed to the establishment of countless organizations of education and research. On a personal note, the lives and careers of so many of us, hundreds on this call alone, would never have been the same without Raj. So for all these reasons, we are excited to celebrate Raj today and to start this lecture series in his honor. Moving forward with the program, Raj, we have a bit of a surprise for you today. Some of your longtime friends and colleagues have recorded some messages for you. I think everyone here today will see some familiar faces. Let's take a look.
Really, this is a great honor for me to say a few things about Raj. I want to share some personal story. I came to CMU before even I received my PhD from Edinburgh. So I actually spent the time at the CMU and did a lot of experiments, validated the hypothesis of my PhD thesis, then went back to Edinburgh, defended my thesis, got my PhD. Then I joined Carnegie Mellon. I learned how to really pursue world-class research with the passion and the sense of purpose from Raj. So that sense of purpose make this award more effective, help people to communicate better, started with my CMU days. So thank you, Raj, for your influence, leadership, and the vision. It's profound. I think that technology and pursuit is indeed impacting people throughout the world.
I read and admired his big ideas. He was not just building robots or doing gizmo here or a software here, but he was much more thinking in a bigger way, and I admired it, and I learned from that very much. Raj, congratulations, we survived the old age, and we are still active, and thank God our brains are still working, and we have big ideas, and I think we also have a historical perspective. We have a perspective what worked, what didn't work, and hopefully the younger generation will listen to us.
I first met Raj Reddy in 1975 when I came to CMU. He's done many, many things for me, some of them favors, some of them professional, and I hardly have ever had a chance to thank him. So this is my big shot. After I got here, he taught me a tremendous amount about science administration and how important it is to not prejudge the research of others, but to give them an opportunity to prove themselves. And he gave me an opportunity to prove myself, because after I had been in adjunct status for 17 years, he brought me back to CMU in 1998 and gave me many new opportunities, one of which was to travel the world working on the Universal Library, and another was to run our graduate program in e-business technology. And when that ended, our graduate program in AI and innovation. So he's done many, many things for me, and this is my chance to look him right in the eye and say, thank you, Raj.
Hi, Raj. I'm delighted to be here to say thank you. When I came to CMU, you opened my mind for what AI could do. I learned from you to be a visionary, to be a problem solver, to be a long-term thinking, and to change the world. Thanks, Raj, for everything, and good luck for all the rest of your life.
You don't need me to talk about Raj's achievements. What I would like to share is how caring Raj is for his students. I'm so lucky to be one of Raj's students. Raj's caring and support for his students is far beyond a PhD supervisor. All throughout my career, Raj Reddy has always been there whenever I need help. He even proactively looks out for me in any possible way that makes me more successful and a better person. Just last month, he called to coach me how to make the impact of Microsoft Research Asia better known outside China. There's an old Chinese saying, teacher for one day, father forever. To be a Raj student is such a privilege. I'm so honored to be able to look up to Raj as my father figure. Thank you, Raj.
Raj is one of my friends that I value most deeply in my life. We met on the first day that I was a professor at Stanford. I went to John McCarthy's time-sharing laboratory to look around, and there I met a graduate student displaying speech waveforms on a PDP-1 mini computer display. That was Raj, energetically pioneering AI's speech understanding problem, work that amazingly these days we all take for granted. When it came time for Raj to explore the academic world beyond Stanford, I urged Raj to accept CMU's offer because there he could work with and learn from three of the great pillars of early computer science, Newell, Simon, and Perlis, all of whom, of course, became Turing Award winners. At CMU, Raj became the fourth great pillar of the department. Speech, robotics, dean of the school, great leadership, and of course, yet another Turing Award for CMU. Remarkably, Raj is also the most significant computer science humanitarian that I know. His high awards from the government of France and especially the government of India, his Japanese Honda Prize, and other awards are unmatched among our colleagues. Raj is a model for young scientists to emulate. Raj, live a long and happy life. We all need you.
That was wonderful, and thank you to everyone who participated. I think that gives a powerful view of Raj's influence on so many of us and on the field. Next up, we'll hear from CMU's 10th president, and of course, a computer scientist himself and a member of the SCS faculty, Farnam Jahanian. Farnam?
Thank you very much, Marshall. Thank you very much, Marshall. Hello, everyone, and it's good to be with you. Thank you for joining us. I hope you and your loved ones are staying safe and well. I do want to take a moment to thank Martial Hebert for his leadership of our computer science school, which continues to build on the foundation that's created under stewardship of the former deans of our Dean of SCS, Nico Haberman, our honoree Raj Reddy, of course, Jim Morris, Randy Bryant, Andrew Moore and Tom Mitchell. Marshall, your leadership and theirs have been crucial to school's amazing success and vision for the future. In addition to having the honor of serving as CMU president, as Marshall just mentioned, I'm a computer scientist and a proud member of the faculty. So this is quite special for me to be with you and addressing this group of thought leaders and innovators in our field, as well as, of course, countless number of faculty, students, alumni, and who are with us today to celebrate, of course, the incomparable Raj Reddy and his contributions over the years. I want to extend a special welcome to Raj's family and friends, especially his wife, Anu, who has been a long-term member of the Carnegie Mellon family. I'm also grateful to Harry Shum for serving as our MC today, and to our three esteemed keynote presenters, Yoshua Bengio, Jeff Hinton, and Yann, LeCun, from whom you will hear later on today. As everyone on this webinar knows, our entire world is adapting to breathtaking technological advances and unprecedented access to data that are rapidly transforming our economy, our society, and our culture. These advances are underpinning our economic prosperity, accelerating the pace of discovery and innovation across nearly all fields of inquiry. Computer science at CMU has played a disproportionate role in bringing about this revolution over the last 60+ years. And in particular, the leadership in the AI area has paved the way for remarkable innovations that we see today. One of the most seminal moments for our field took place in the summer of 1956, when 20 of the brightest minds in computer and cognitive sciences gathered for a workshop at Dartmouth dedicated to exploring the potential for AI. At this 8-week brainstorming session, CMU professors Herb Simon, Alan Newell played leading roles, having already created the first AI program, Logic Theorist, with Cliff Shaw. In the years that followed, and I think you just heard this from Professor Ed Feigenbaum, Newell Simon would unite with Alan Perlis to articulate and advance an expansive view of computer science as an academic discipline, as it was underscored in the 1967 essay in Science. Just imagine, more than 60 years ago, they had the foresight to see AI, human-computer interaction, cognitive psychology, robotics, natural language understanding, and computer vision all as part of this emerging field of computer science. And around the same time, they established CMU's computer science department with this philosophy at its foundation. The rest, of course, as you know, is history. Today, computation and data-intensive approaches extend well beyond the School of Computer Science and are embedded across the university, including in sciences, engineering, business, policy, humanities, and the arts. In the long history of groundbreaking achievements that have defined, I should say, computer science and CMU in the last 50 years, there's perhaps no thought leader more impactful than our honoree Raj Reddy. Raj is truly a living legend, a man who not only had a front row seat to this broad technology and data-driven revolution, but was also responsible for many significant advances, especially in artificial intelligence. Over the span of 50 years, he has worked on historic demonstrations of AI's power to enhance humanity. In particular, he has long been recognized for his work to pioneer the field of speech understanding. Much of the work that we do today, we see, and innovations that we see in speech recognition and speech understanding can trace its lineage back to Raj's work and his collaborators. As you heard just now, in 1994, Raj Reddy and Edward Feigenbaum, from whom we just heard, won the ACM Turing Award, the highest honor in computer science. Their citation highlighted the joint work they had done, pioneering the design and construction of large-scale artificial intelligence systems, demonstrating the practical importance and potential commercial impact of AI technology. In recognition of his incredible achievements, Raj has amassed a long list of, I should say, honors that would probably take a whole session to review. In addition, of course, to the Turing Award, the Okawa Prize in 2004, 2005, Honda Prize, Vannevar Bush Award in 2006, fellows of many societies, of course, a member of the National Academy of Engineering, National Academy of Arts and Sciences, and as you just heard from Professor Feigenbaum, Raj has also been recognized by President of France in 1984 by the Legion of Honor Award and the Padma Bhushan Award by the President of India in 2001. To this day, Raj continues to dream big. All you have to do is to go to his office and just talk to him about things. And I do that periodically, and every time it's an enjoyable conversation. In fact, recently he's been espousing an idea called guardian angels, or intelligent angels that could be deployed to ensure user safety, security, and well-being. The year 2020 is the perfect time for such a concept. Once again, Raj is proving to be a man for our times. Just like his influence on the discipline, his impact on Carnegie Mellon is immeasurable. Over the past 50 years, Raj has been instrumental in shaping School of Computer Science into a leading school, not only in computer science, AI, and robotics, but through its connections with other disciplines. As I'm sure you know, he served as the founding director of the Robotics Institute from 1979 to 1991, and the dean of the School of Computer Science from 1991 through 1999, at a very critical point in its growth and its evolution. It would be hard to overstate how Raj Reddy's leadership and contributions have amplified CMU's global reach and impact. During his tenure as dean, he recruited countless faculty and students and scholars, helped win funding for dozens of research projects, and founded the Institute for Software Research. He was also instrumental in launching both our Qatar and Silicon Valley campuses. His leadership built on the vision of Newell, Perlis, and Simon of what academic computer science should be, and created a model environment for innovation that's emulated far and wide. This broad vision of computer science and AI, with Raj as its champion, has informed and helped the aspirations of the whole world for what AI could do for humanity. And as you just heard in the video, his most lasting contributions may be the generations of scholars who continue to learn from and be inspired by Raj Reddy, including Marshall, our MC, Harry Shum, and our three keynote speakers. I think it's fair to say that whether you're formally advised by Raj Reddy or simply admired by his example, we're all Raj Reddy's students. Raj, on behalf of the entire Carnegie Mellon University community, I want to extend my sincere congratulations and deep gratitude to you for your incredible 50 years of service and legacy of achievements, which has contributed so much to the discipline, to the School of Computer Science, to Carnegie Mellon, and indeed to the world. As I turn the virtual podium over to Raj for a few remarks, wherever you are, please join me in extending a warm virtual round of applause for our friend and mentor, Raj Reddy. Raj, the floor is yours.
I want to thank Harry and Marshall and Farnam for their kind words, and many others from on the video. I'm also thankful to Joshua, Jeff, and Yann, who have joined us on this occasion despite their busy schedules. I was fortunate to have met and worked with many of the founding fathers of AI early on. I met John McCarthy, Marvin Minsky, and Ed Feigenbaum while I was a graduate student at Stanford. When I came to CMU in 1969, I met the other two founders of AI, Alan Newell and Herb Simon, as well as Alan Perlis, who was the direct head of the computer science department and the first Turing Award winner. Even though Newell, Simon, and Perlis were superstars in their own right, they were able to subsume their egos and work together to create a world-class environment at CMU. They nurtured the culture and ethos of our environment, which continues to today. In 1969, the computer science department was small. There were only 9 faculty members. The whole department was in one corner of Porter Hall. Today, that small department has grown into the School of Computer Science with 7 departments and over 270 faculty members. Out of these modest beginnings came the cars that drive themselves, smartphones that see, hear, speak, and answer questions, speech-to-speech translation, and world champion chess and poker machines. I have been blessed by having the opportunity to work with many brilliant colleagues, too numerous to mention here. But I do want to make a special mention of Jamie Carbonell, whose untimely loss earlier this year was tragic. He was a pioneer in language technology and machine learning, and central to our research in AI at CMU. He once famously said that the primary goal of AI research is to get the right information to the right people at the right time in the right language. He called this the AI Bill of Rights. He was a good friend and great colleague, and he will be missed. Lastly, I want to make a few comments on the future of AI, in particular, human-centered AI and learning-centered AI. In the recent years, there have been predictions of AI becoming an existential threat to humankind. I do not agree. In the past 60 years, I have never heard any of the leaders of AI, including Newell and Simon, talk about AI replacing or displacing the humans on this planet. From a historical perspective, AI is just a continuation of technology development through the ages with the goal of enhancing human capabilities. While I'm optimistic of the potential of human-centered AI to enhance the human mental capabilities, we must acknowledge that there is a potential of these systems to reflect and perpetuate the human biases as well. Important work is being done in this area at CMU and other places, and it's my hope that CMU will lead the way to ensure that the AI is a tool for inclusion and equality rather than bias and discrimination. The success of deep learning systems has forever transformed the paradigm of AI research. All the future AI research will be learning-centric. Computers, that is, the computers will learn to do various human tasks rather than being programmed. We are just at the beginning of this endeavor. We do not yet have systems with human-like capabilities that learn from examples, learn by doing, learn by discovery, as well as learn from mistakes or learn from a teacher sitting in a classroom. Given the unlimited computation and unlimited memory, I think it will become possible to solve all such problems. It is just a matter of time. Whether it will take 100 years or 1,000 years is not relevant. After all, we are attempting to enhance the human cognitive capabilities that has taken evolution millions of years. Thank you. Happy and healthy holidays. Marshall will now introduce our speakers.
The three speakers will now each give a brief presentation and then come back as a panel to answer your questions. First up is Professor Yoshua Bengio. He is a professor of computer science at the University of Montreal, founder and scientific director of MILA, Quebec's AI Institute, fellow of the Royal Society, and recipient of numerous awards in addition to the Turing Award. Yoshua?
Thanks, Marshall. And thanks, Raj, and everyone who's been today giving us these very warm words. So let me share my screen. I want to tell you about a research direction that my lab has taken in the last couple of years that is attempting to go beyond some of the limitations that we see with current machine learning. And you see some of the people who have been working with me on these projects. So deep learning of conscious processing, where does that really start from? It starts from thinking about our even basic learning theory, which assumes things that are maybe too strong, that the test data will be from the same distribution as the training data. And I think we have started to move away from that assumption and start thinking about not just one distribution from which the data comes, but the idea that there will be changes in distribution. And really, we want our learners to do a good job out of distribution. And so one of the themes that we've been exploring is what can we do to help a learner generalize out of distribution? How could we even be sure that it's going to work? Because it could be potentially anything. And of course, the idea is that the changes in distribution that are happening in our world as human beings or that are facing robots are not random. They come because there are changes that are happening in the world. And the way that we're able to deal with those changes is by reusing pieces of knowledge that we have already acquired. And so this notion of how to represent knowledge in something like a deep net in a way that favors this modularization and reuse is one of the themes that we are exploring. This is also connected to the notion of systematicity and systematic generalization, which has been studied a lot in linguistics. But more recently, people have been trying to think about this more generally. In the image, what you see is you can make sense of the picture with this strange vehicle because somehow you already know these other vehicles that it borrows some concepts from. And what's interesting is that the notion of generalization we're talking about here makes sense even though you may have never seen anything like this, or even if you had an infinite amount of data in your training set, you might never see something like this. But yet humans are able to generalize to these things. For example, if I give you a science fiction scenario that's unlike anything you've seen before or you've lived before, or simply if you start driving in an unknown city or where the traffic laws are very different, you're somehow able to cope. Current deep learning and in general current machine learning is not doing very well at these kinds of things, but humans are doing very well. And so one of the themes of my work is what can we get in terms of inspiration from humans when they face this novelty, these changes in distribution. It turns out that what humans do seems to be switching to a very different kind of cognitive processing. We don't follow our habitual routines. We suddenly start thinking about the problem. We focus our attention on what is going on, and we are able to reason in order to find solutions. And those solutions aren't always very they're very creative, but they're not very fine-tuned, as I would say. But they can be the basis of further habitual routines as we practice in this new environment. I believe this is connected to a division of labor in the types of tasks that humans look at that Dan Kahneman has discussed in his beautiful book on Thinking Fast and Slow, where he talks about a system 1 and a system 2. So the system 1 is intuitive, fast, happening at an unconscious level, happening in parallel. It's hard to explain verbally what is going on there. We don't have access to that. And there's a lot of knowledge about the world which is captured at that level that is implicit because we can't communicate it. And deep learning as it stands today is very good at these things. Whereas system 2 cognitive tasks are those I mentioned earlier, which require conscious attention, usually go through a sequence of steps. They're logical. We're not very efficient at doing these things. It takes us a lot of time. But this is how we program computers right now with algorithms. This is how we plan and reason. And it's about aspects of the world that we can describe verbally. So it's all about explicit knowledge. And we'd like to build these capabilities into deep learning. And to go back to my first slide, the important point here is that this system 2 abilities allows us to manipulate those high-level semantic concepts that we can communicate in a way that is novel, that can recombine the old concepts in novel ways, combinatorially expanding the power of generalization. So this is what we're trying to do. What it says about the world that we're trying to exploit is that there are aspects of the world that are verbalizable and aspects that are not. And so one of the questions I've been asking is, if we want to build machine learning systems that are going to do a good job on those aspects that are verbalizable, the system 2 aspects of the world, what are the kinds of inductive biases, the kind of priors, the kind of properties of that type of knowledge that we could exploit and put in the machine learning architectures and training frameworks to help them do a better job? Now, one question that comes up when I give these kinds of talks is how is that related or different from the classical AI, symbolic research, symbolic rule-based program that has dominated AI for many decades in the 20th century. And I guess the general idea is we'd like to have the advantages of both the machine learning, deep learning approaches of recent decades, as well as some of the advantages of the good old-fashioned AI. So we don't want to lose the things that we've gained with modern deep learning and machine learning. Like, we need efficient large-scale learning. We want to make sure that our high-level concepts will be grounded, will have a meaning anchored in low-level perception and action. We want to keep the power of generalization of distributed representations that Jeff Hinton has brought beautifully to our research community. We want to be able to deal with some of the issues of classical good old-fashioned AI that are bounded by expensive search, using some of the system 1 neural nets to efficiently generate hypotheses without having to look at trillions of trajectories. And we want to be able to continue handling uncertainty as we're doing in modern machine learning that's based on probability. But we want to bring in systematic generalization. We want to bring in the ability to factor knowledge into small exchangeable pieces, giving rise to this combinatorial advantage. And we want to bring in indirection, variables, the notion of instances and types and references and so on. So that's the goal. One of the important connections, of course, when we talk about conscious processing is the one with language. Very often we are able to take our thoughts and convert them to language. In fact, this is how we know that somebody is conscious. We ask them to report what they're thinking about. And so this suggests that those high-level representations that system 2 is manipulating have a strong connection to language. But that's not enough to really give meaning to the words that we manipulate with language. As I said, they are anchored in low-level perception and action. That means that I think for the future of natural language processing, we should be making sure that we do grounded language learning, as we've started and others have started to do in our field. The last slide here is a list of, a first list of inductive biases that my group and others are exploring that fit well with what we know about conscious processing, especially through a language, and that can be transformed into particular architectures or particular training frameworks for these high-level cognitive abilities that we want to put in deep learning. I'll only mention one, the sparse factor graph. It's the idea that the high-level knowledge is broken down into small pieces, and that these pieces only refer to very few variables at a time, just like a sentence in natural language. So thank you very much. So now I'll give back the turn to Martial.
Thank you, Yoshua. Our next speaker is Professor Jeff Hinton, Emeritus Professor of Computer Science at the University of Toronto. He is also the Chief Scientific Advisor of the Vector Institute and a VP Engineering Fellow at Google. He was a faculty member at CMU from 1982 to 1987, and at that time he published and conducted foundational work on the concept of backpropagation. Jeff?
First, I'd like to thank Raj Reddy. When I was at CMU, he was extremely helpful, not only in discussing speech recognition, but he also created a job for my wife, which is the kind of thing only Raj could do. Today, I've decided to talk about a particular technical issue in neural nets, rather than give some very general overview. Okay, so what I'm going to talk about is the idea of fast weights. If you look at biological systems, they adapt at many different timescales. Most of the neural nets we use only have 2 or 3 timescales. There's the timescale of the neural activities, which change at each time step as you present new examples. There's the weights that change slowly over many time steps during the learning. And then sometimes the architectures evolve over many different trainings. So that's a bit like evolution. What I'm going to talk about is what happens if we add another time scale to the weights. So the idea of fast weights is that on each connection, the total weight is the sum of 2 different components. One component is the standard slow weight. This learns slowly with training examples, and it may also decay slowly, and that holds the long-term knowledge of the system. That's the kind of weight we're familiar with. What I want to add to that is an additional fast weight, which is a kind of overlay on the slow weights. And this fast weight learns quickly and decays quickly. And that's where we can hold temporary knowledge. So some evidence that people have fast weights comes from priming. If you hear the word cucumber, and then a few minutes later, I ask you to recognize words that are disguised by a huge amount of noise, you'll be slightly better at recognizing the word cucumber because you heard it a few minutes ago. That's called priming. Now, the question is, how do people do that? It's possible they maintain a pattern of neural activity that represents that cucumber occurred recently. But of course, they'd have to retain patterns of neural activity for all the different words that occurred recently. We could do that if we had 1 neuron per concept, but that seems unlikely. In that case, we'd do it by just lowering the threshold of the cucumber neuron. We can also do it if we have distributed patterns of activity that act as point attractors for each concept. And what we do then is we change the weights between the active units in the distributed pattern of activity so as to make an attractor a bit more attractive. If you think in terms of energy, you make that energy minimum a bit lower in energy. Changing weights to store memory has a big advantage over changing activity vectors. Weight matrices have much more capacity. Even if we use a very primitive storage rule, like the outer product rule that you can use with one-shot learning, as in a Hopfield net, we could store 100 different attractors quite easily in a 1,000 by 1,000 matrix. What this does is it frees up activities so that we can use the neurons for processing the current input rather than for storing memories of things that happened recently. What I'm going to talk about now is a very peculiar effect you get from these fast weights. And it's research I did at CMU. So it's very old research. I did it with David Ploud. Suppose we use many passes through our training set to learn associations between input vectors and output vectors, and we use backpropagation in a feed-forward neural network. Then after training, we switch to learning a new set of associations without continuing to train on the old ones. What will happen is we'll get interference with the old associations, often called catastrophic interference. The old associations will become blurry. And it looks as if the old associations have disappeared. But actually, the old associations are still there and you can get them back. And if you use fast weights, you can get them back without destroying the new learning. So here's an analogy. If I have a scene and I produce an image from the scene using a projection, I can set up the projection so I get a nice clean image of the screen. If I now add blur to the projection, I get a blurry image. But by looking at the blurry images, I can estimate the inverse of the blur. And so I can add both the blur and its inverse. And now I'll get back a sharp image of the scene again. And that's an analogy for what we're going to do with learning in a neural net. We're going to learn to map from input to output with a set of weights W. Then we're going to do some new learning on different data, and that's going to add noise to the weights. And we assume the new data has nothing to do with the old data, so we can treat it as random noise added to the weights. Then if we want to get back the old associations, what we need to do is estimate the inverse of that noise. We need to add something else that cancels out the noise in order to get the old associations. So when you train a neural net, what's happening is you're reducing the error. So in these pictures, the vertical axis stands for the error, and the horizontal axes are the weights. So this will be a neural network with only 2 weights. And as we train the neural network, what we're doing is we're wandering down a ravine. It's almost always like that. If we now add some random noise to the weight vector, by, for example, training on a completely different set of associations with a different error function, that'll act as random noise to the weights. And that will make our performance much worse. But the set of weights that we get to, that red dot in the middle image, is actually closely related to the green dot. It's closely related to the set of weights we had when we could do the first task. If you now take a subset of the training examples from the first task and you relearn on that subset, what happens is all the other training examples will get better. So here's a little picture of what happens. You first train on one task, then you train on a randomly related task, so your performance on the first task gets worse. Then you start retraining on 50% of the training examples from the first task. And of course, the ones you are retraining on, the error goes down, but also the ones you're not retraining on, the error goes down. This is actually much like what happens to someone who learned a foreign language when they were young, didn't speak it for the next 50 years, and then goes back to that country and starts speaking the language again. What they discover is that they don't know the names of anything, but after a short while, the names all come back, and not just ones they practice, but all the other ones come back too. And this happens in the second graph, even if you only retrain on 10% of the data you knew before, the other associations come back, even though they're randomly related. So we managed to get back the knowledge we had before. Now, if you just do that in the slow weights, what you'll do is you'll lose some of the new knowledge. But if you do the retraining in fast weights, so you just temporarily do retraining, then the knowledge won't be lost in the slow weights. We'll have an overlay of fast weights that kind of cancels out what's happened since we learned that stuff. And so we'll be able to get back our old knowledge without losing our new knowledge. This can help to explain the Poincaré effect. I used the Anglo-Canadian spelling, so I'd know how to pronounce it. Poincaré reported the following effect. You think hard about a mathematical problem and you can't find a solution. The next day, I believe while stepping off a bus, Poincaré, the solution suddenly came to Poincaré without having thought about it in between. Now, Poincaré interpreted that, or other people have interpreted that, as you unconsciously have been thinking about the problem and you reach the solution unconsciously. I think there's a much more plausible explanation of that if you appeal to fast weights. So at any one time, you have your slow weights, which are your long-term knowledge. You also have an overlay of fast weights. And as time varies, the next day, for example, you'll have a different overlay of fast weights. And sometimes the overlay of fast weights will make it easy to see things and sometimes not. You see the same thing with the tip of the tongue phenomenon for people's names. You try and remember the name of somebody, especially if you're old, and you just can't and you don't know why. And then the next day you try and remember the name and there's no problem. And it's not like you were unconsciously thinking about this problem all the time in between. It's just your fast weights are slightly different. So I want to conclude by just talking about some of the other uses of fast weights. And people in neural nets are beginning to use them now. It's taken 30 years, but there you go. Fast weights can act as a temporary memory that allow neural networks to be really recursive. So for the kind of stuff Yoshua was talking about, we'd like truly recursive neural nets. And what I mean by truly recursive is that you can reuse the same neurons and the same weights for the recursive call of a function. Now, in order to do that, you have to free up those neurons from remembering where you were in computing the high level call of the function, all the temporary information you had, so that you can use the neurons again for the recursive call. To do that, you need a memory, and fast weights can act as that memory. And in fact, as a historical anecdote, the very first talk I gave about neural nets in 1973 was about how you use fast weights to make neural networks recursive. I haven't got around to publishing it yet, but I'm planning to do that soon. Fast weights can also improve mixing when training Boltzmann machines. They can give a recurrent neural net much more memory capacity, so make recurrent neural nets work better. There's a paper by Barr and others in 2016 on that. They can also speed up learning by doing a look ahead. So the idea is, suppose you had an army that had to get through rough terrain. You wouldn't try and drag the whole army over rough terrain while you didn't know which way to go. You'd send out scouts to find a good way to go, and then the scouts would tell the army to come that way. And the scouts could do much more exploration without changing where the army was. And so if you're learning, you'd like to see, how might I change my weights so as to get better without actually changing the weights yet until you find a good way to change them. And that's what you're doing in a look ahead search. Okay, I think I've managed to convey one interesting idea about using fast weights, one weird phenomenon you get with them, and one good use of them for doing recursion in neural nets. So I'll end there.
Thank you, Jeff. Our last speaker is Professor Yann LeCun. He is Silver Professor of Computer Science at NYU and Chief AI Scientist at Facebook, where he created Facebook AI Research in 2013. Prior to that, he held research positions at NEC, AT&T Lab Research, and Bell Labs. Yann?
Thank you, Martial, for the introduction, and thank you for inviting me to participate in this event. I have Carnegie Mellon has a special place in my mind, and I'll tell you in just a minute why. So the title here of my talk is actually stolen from a talk that Raj Reddy gave a few years ago, and this is really the idea that a machine can be made intelligent by learning as opposed to being programmed. And I can't help but thinking that CMU has been sort of influencing me, even if I wasn't conscious of it, since the early days. First, because I learned about Jeff's work when, on Boston machines in the early 80s, and that kind of had a big influence on me. And then Jeff invited me to a summer school at Carnegie Mellon. This is a picture from that summer school. And this was kind of my first experience of an American campus. I think it lasted 2 or 3 weeks. And it was very kind of life-changing for me. I left, I met a lot of people from CMU. I don't believe I met Raj at that time. That was only a few years later. But it was really kind of a changing experience for me. And I realize now that a lot of the things that were taking place at CMU were things that I was interested in. So I started looking at stuff that I'd been interested in and things that Raj has had a big influence on. And there's a big overlap between us somehow, except he has a 20 years head start on me. So, I kind of had to catch up. But, we're both interested in the question of what is intelligence, how to build intelligent machines, getting machines to learn, perceive, reason, act, etc. We're both interested in connecting people with knowledge. So for a while, I was working on a project called Déjà Vu, which was kind of a technology for digitizing documents. And this is in the early days of the internet, so as to bring them to the internet. And around the same time, Raj was working on the Universal Digital Library and the Million Book Project, which in fact ended up using Déjà Vu for a while. And that's what gave rise to a bunch of follow-up projects. So I think that's this idea that technology can be used for good things in society is something that Raj has been pushing a lot, and I'm sort of very admirative of his influence there. And of course, the fact that technology is difficult to use for most people, and it's increasingly difficult because it's more pervasive. So an increasingly large number of people would have the option of using technology but can't because, for example, they can't read. So Raj has been pushing this idea that machines should be able to understand when we talk to them, and they should be able to do, help people communicate by translating and things like that, or give people access to data. Another point of interest for technology is that technology can connect people with each other. And of course, I work at Facebook. I'm also a professor at NYU, but I work at Facebook, and Raj is being sort of talking about this problem that we have a wealth of information and a scarcity of attention. And a lot of the work that companies like Facebook, Google, etc. are doing is, basically kind of selecting information for people. It's very difficult to do this in ways that are useful and productive in the long term. But it involves things like language translation, which of course Raj has been interested in, and things like telepresence, which also Raj has been talking about. And then down the line, I think we can talk about things like virtual assistants. And so Raj has been proposing those two concepts, COGS and GATS, cognition amplifiers and personal guardian angels, which I guess I would include driving assistance systems in that. So that kind of connects with autonomous driving and robotics. And really we can imagine a future where people will have those virtual assistants basically always available, perhaps in the form of a augmented reality glass or something like that. And so people, will have access to the entire world knowledge and each other instantly. The other thing that I've been following on the footsteps of Raj and others at CMU, like Tom Mitchell, is the idea that deriving knowledge from data is actually kind of a field of investigation and should be a discipline, an academic discipline. So CMU was really a pioneer in creating the machine learning department, following the CALD, the Center for Autonomous Learning and Discovery. And at NYU, a few years later, I started the Center for Data Science, which really has kind of the same motivation. So with that introduction, Raj, in one of his talks a few years ago, was kind of reflecting on this part of a paper from, the Turing's famous paper, where he says that really, if we build intelligent machines, that, it was kind of a set of conjectures. We should really build the mind of a child so that the machine would be able to learn and train itself. And I think that's what we're doing at the moment. That's one of the things that's been driving me to work in AI and in machine learning in particular, following on the footsteps of Geoff in particular. And so I was a postdoc with Geoff in 1987, 88. And then I moved to Bell Labs. And around the same time that Raj was working with Kai-Fu Lee on speech recognition using hidden Markov models, the statistical models that Kai-Fu was mentioning in this video, I was working on using machine learning, statistical methods as well, you can call them that way, for character recognition. Why speech and character recognition? Back in the 1980s, these were the only two domains where we could collect enough data to actually do anything with machine learning. There was no internet, so there was, data was rare, and these were the two applications that had kind of obvious practical applications, but also it was possible to get data. So, fast forward to today, deep learning is used for all kinds of different things. One thing that I find particularly satisfying is that it's used to save lives. So almost every car now that comes out, at least in Europe, has what's called automated emergency braking systems. So it's basically a little convolutional net that looks out the window and brakes if there is an obstacle in front of the car. And this, according to some statistics, this reduces collisions by 40%. That includes collisions with pedestrians, for example. And then there is a lot of applications, of course, of deep learning in medicine and content filtering hate speech, call to violence, terrorist propaganda, misinformation on election and public health. No company can claim to do a perfect job at this, but everybody is trying. Connecting people with each other and with information is something that will require a machine to be intelligent, because they're kind of required to interact with us. And I'm going to show you some examples of the state of the art in some areas of AI. But first, kind of repeat a little bit what Yoshua mentioned, which is that we really have two main problems in AI today. The third one I have no idea what to do about. But the first problem is that we have lots of data, but a small proportion of it is labeled. And so it would be nice to be able to get machines to learn a bit like humans and animals without requiring a lot of labeled data, basically by just using unlabeled data or a small amount of labeled data. So using self-supervised or unsupervised learning as opposed to purely supervised learning. The second thing is learning to reason, which is the question that Yoshua kind of addressed. So one big question, I guess, that we must answer is how is it that humans and animals learn so quickly? And humans learn mostly by observation, at least in the first few months of life. And they learn sort of very basic concepts about, about the world, like intuitive physics and things like this. And the equivalent for machines would be to get machines to watch videos all day and figure out how the world works by just watching videos. And perhaps this would be kind of a way for some sort of common sense to emerge from machines. This is very speculative, of course, but that's kind of a hope. One way of approaching this problem is to use what I call self-supervised learning. So it's really a branch of unsupervised learning, if you want, but it's using similar techniques as supervised learning, basically using a piece of the input to supervise a supervised system to predict that piece of the input that the system pretends doesn't know. So you show a machine a segment of video, for example, and you show it just the beginning of the clip, and then you ask it to predict the end. And of course, you show it the end so it can train itself to do a good job at the prediction. And the main issue there is how to represent uncertainty in the prediction, because many things can happen in a video, and you don't want the machine to just make one prediction. That's the technical problem that we need to solve. And we don't quite know how to solve, although we have several approaches that kind of work. In particular, one that works really well is in the context of natural language processing. And it's using a technique that I worked on during my PhD and that Pascal Vincent in Yoshua's lab actually worked on a little over 10 years ago, called denoising autoencoder. So the idea there is that you take a piece of data, let's say a piece of text, and you corrupt it, you remove some of the words, and then you train some large neural net to predict the words that are missing. And in the process of doing so, the neural net basically learns a good representation of text, because to be able to predict missing words, it needs to kind of have some understanding of what the text is about. And so that has been astonishingly successful in the sense that it has revolutionized natural language processing over the last 2 years or so. This uses a concept called associative memory or differentiable associative memory, which are built into an architecture, a neural net architecture called Transformer, proposed by Waswani at Google a couple of years ago. And then this idea of using this kind of self-supervised learning process to pre-train it really with unlabeled data is from another series of authors from Google, Devlin et al. A couple of years ago. And this really truly revolutionized NLP. So those networks are really large, and they can be used to learn multilingual representation of text. This is some work from some of my colleagues at Facebook from a while ago. And those systems can learn to kind of represent text independently of language. I don't really have time to explain how this works. But this has led to incredible progress in translation, which is something that Raj is really interested in or has been interested in the sense that you can now train very large neural nets with billions of parameters to translate a large number of languages, about 100, into another 100 languages. And you don't need to have parallel text for every pair of language. And you may only require to have a very small amount of text for each language. So this is astonishing progress. This is some work from Facebook that is actually open source that you can play with. And it's used in production at Facebook for large-scale language translation. There's also been a huge amount of progress in speech recognition, which is what Raj started his career working on. So nowadays, those transformers combined with convolutional networks are used for speech recognition, and they basically can learn the task end to end, and you can use self-supervised pre-training to train those systems. This is a series of work also at Facebook that shows that by pre-training with a few hundred hours of speech, you can now get essentially state-of-the-art performance of the speech recognition system with only 10 minutes of labeled data, which is absolutely astonishing. You don't get the state-of-the-art of today, you get the state-of-the-art of last year, okay? And again, this works for multilingual. So you can have a system that can recognize 14 different languages, 12 different languages with basically state-of-the-art. And that combined system works better than if you train individual systems to recognize individual languages, which is also astonishing. So a huge amount of progress. Same in dialogue systems. Dialogue systems, unfortunately, at the moment are entertaining, but not particularly useful. They can tell you facts about, that they get from Wikipedia or something, but they're a little shallow. So I don't think they've passed the Turing test. Although in this little dialogue, it would be difficult for you to tell who is the machine and who is the human. Other applications of those techniques include things like symbolically solve equations, like differential equations and integrals. This is also very surprising. Some work, again, by some of my colleagues at Facebook, where you give a formula to a machine and it will compute the integral symbolically. And this works just as well or better in certain cases than Mathematica, MATLAB, or Maple. Lastly, in this kind of application is kind of a new way of doing computer vision, which of course, CMU has had a huge amount of contribution, Martial included, in computer vision. So in my opinion, the future of computer vision is also a combination of convolutional net for the front end combined with transformer-like objects to do sort of object-based reasoning. And this is a system that can do dense semantic segmentation. And it's by some of my colleagues at Facebook, Nicolas Carrion, who's now actually a postdoc at NYU. And it's basically trained end-to-end to do semantic segmentation, generate masks for every object, put a name on it, and give you a score. I think that's really the future. Now, there's been a lot of work recently, and I'll end on this, on sort of what's called contrastive embeddings and other self-supervised learning applied to image recognition to learn features for images. There's been a huge amount of progress over the last year or two on this by people at Google, Facebook, and others. Starting with actually the root of that is some work I did in the 90s and Jeff and my group also in the mid-2000s on so-called metric learning. And the idea there is that you can train a system in a somewhat self-supervised manner without label data to learn good features for images. They use different techniques than what's used for NLP, mainly for the reason I mentioned earlier, that it's difficult to represent uncertainty in prediction for images. But this works astonishingly well, and has been sort of a huge success with kind of in only the last few months, essentially. Let me end with conclusions. So I think self-supervised learning is really the future. And I need to tell you a story about Jeff. When we first worked together and talked, I was very kind of skeptical about unsupervised learning in general, because I didn't know how to define it properly. But I completely changed my mind about 15, 20 years ago, and basically rallied to his cause that the only way forward for machine learning is using unlabeled data. Reasoning planning, I'm not going to talk about this because Yoshua already did. And I just want to make a point. We hear a lot about artificial general intelligence. And as Raj said, there is a lot of fears about it, and they are completely unsubstantiated. I don't think there is such a thing as general intelligence anyway. Even human intelligence is very specialized. And so I don't think we should be talking at all about AGI. We should be talking about human level AI. Thank you very much. And I guess I call Harry and Jeff and Yoshua and Raj for the panel discussion.
Thank you very much, Yann, Jeff, and Yoshua and Raj for your wonderful lectures. I want to get this Q&A session very exciting. So if you don't mind that I pick up, what Yann just left, half controversial statement that there is no such a thing called AGI. To get it even more exciting, Jeff, if you don't mind, let me quote your tweet from June 11th, where you said, Jeff, you said that extrapolating the spectacular performance of GPT-3 into the future suggests that the answer to life, the universe, and the everything is just the 4.398 trillion parameters. So I want you to just help us understand, did you really mean it? How did you come up with this funky number? I actually calculated that if we divide that number by 175 billion parameters, it's actually not a big number. So did you suggest that we actually approaching AGI, did you agree with what the Yann just said?
It's actually a joke. The number I gave you is 2 to the 42.
2 to the
in
42.
the novel The Hitchhiker's Guide to the Galaxy, the answer to life, the universe, and everything is 42.
It's 42, yes. So it's not that far. So you agree with Yann that so the AGI is not really there. It's really we should talk about human level intelligence instead.
Let's see. I always try to disagree with Yann. So I'm very ambivalent about whether we're going to get AGI. I just don't know. I think we probably are, but I think it's going to be further off than some people think.
Wait. Did you mean, when you say AGI, did you mean human level intelligence, or you mean
human level intelligence? Yeah, human.
Well, but that's the problem. What Yann is saying is, let's not confuse human level intelligence with general intelligence, which seems something that doesn't make any sense with our understanding of what machine learning is about.
Exactly.
Oh, well,
I think we're going to reach human level intelligence. It's just not general.
Okay. Now, I thought the sort of definition of general intelligence was what people do.
No, we're not good at everything, right?
Right, but there's a whole bunch of things we call common sense or getting by. And that's normally what people mean when they say general intelligence, I think.
If there is one thing we learned over the last few years is that humans are absolutely terrible at Go. Machines are much better. So that means we're not general, we're specialized.
I think I have to stop you guys here. Otherwise, you know, this panel is going to last much longer than what we have. So I have a lot of questions pre-submitted, but I see a couple of very exciting questions from the live Q&A. I'm going to pick one. So this is actually for Jeff. So Jeff is in talking about the tip of the tongue and the Poincaré effect. What is your theory of the function of dreams in sleep in human neural processing? Did you have a model of dreams and how they might play a role in the Poincaré effect?
I do have a theory of dreams. In fact, I've got 3 different theories of dreams, which seems rather too many. Initially, when Terry and I did Boltzmann machines, the idea was that the negative phase of a Boltzmann machine, when you're estimating a partition function, was what dreaming was for. And that actually came from a paper published in Nature by Francis Crick and Graham Mitchison that showed that Hopfield nets, I mean, it was inspired by the fact that Hopfield nets could store more memories if you had a phase where they unlearned. That was all just heuristic. And what Terry and I did was showed that actually having an unlearning phase could be interpreted as a maximum likelihood learning procedure in the Boltzmann machine learning framework. So that was the first theory of dreams. A second theory of dreams was published in Science in about 1995. And that was the idea that you have a recognition model where you go from data to an internal representation, and a generative model where you go from the internal representation to data. And each model is used to train the other model. So in the generative model, you generate top down from data, and it's a directed model. And that's what dreaming was. And what you do during dreaming is you learn to invert the generative model. You learn how to take a low-level representation and reconstruct the high-level representation that caused it. And what you do when you're awake is you learn the generative model. That theory also has a lot of problems. It's a cute theory, but it has a lot of problems. I've got a more recent theory with Terry Sinofsky that what's happening in at least deep sleep or slow wave sleep is that you're trying to do contrastive learning. And one way to do contrastive learning for sequential data is to, you want your representation of the current video frame to be similar to your representation of the next video frame. This is called slow feature analysis, but dissimilar to more distant video frames. You want to do it all in the same sequence, because if you use a different video, they're just hopelessly different anyway. But for a given video, you'd like to say contrast the next frame with the frame that occurs, say, 5 time steps into the future. And you'd like to be more similar to the next frame than you are to the frame that occurs 5 time steps into the future. And one problem for this is how would the brain do that? And one way to solve the problem is to say that while you're awake, what's happening is you're just trying to make the representation of the next frame be similar to the representation of the previous frame. So that's easy. You do that when you're awake. When you're asleep, you're going to try and make the representation of the video frame that's 5 time steps ahead be different from the representation of the video frame that was 5 time steps in the past. And one way to do that would be to replay things at high speed. And the interesting thing about sleep spindles is that it looks as if when rats run through a maze, when they think about it afterwards, they replay the sequence at 7 times the normal speed. So in sleep spindles, what's happening is sequential stuff is happening much faster. And nobody really knows why. Some people think it's so you can replay stuff faster.
Yeah.
But the contrastive learning idea says, well, that's just what you'd need if you wanted to contrast with frames that were a bit more distant in time. If you want to get that into the same window, what you do is you just play the experience much faster.
Yeah.
Now,
so Jeff, I probably have to stop you here.
Yeah.
And so hopefully, we can get a few more questions, from you and the other panelists. So, so if you don't mind, let me pose the second question. This one is actually for Yoshua. So Yoshua, this is a PhD student from CMU doing computer music research. He's currently using deep learning model to generate music, which he found much harder than the common language generation problems. And in particular, it's hard to evaluate. Do you think your conscious model can help generate a better representation for music?
That's a good question I don't have the answer to. I actually worked on music generation a few years ago with Douglas Eck, actually, and it's indeed, it has a different kind of structure than natural language. In particular, it has a lot of these very long-term structured dependencies that, you see, for example, the beginning of the song and the end of the song, and other structure that repeats over very long time spans that current, at least in those days, we were using RNNs and they didn't work very well. But one of the tools that is coming in association with the stuff I talked about, conscious processing, is attention and memory, right? So there's a lot more of attention and memory elements in things like transformers today. And I suspect this is going to really be helpful for dealing with representing structure in music. I don't know if there's recent work in that direction, but this is something to investigate.
Great, thank you, Yoshua. My next question is for Raj. So Raj, what is something that has surprised you in the development of AI in the last 10 years, and also in the last 50 years? You have seen them all, Raj.
I was I used to say, unlimited, unrehearsed, spontaneous speech from open population is an impossible problem. It won't be solved in my lifetime. But with deep learning, both Apple and Microsoft and a number of groups have demonstrated that they can take any arbitrary speech and from anybody and recognize it. And Siri is a good example. And so is Cortana and others. So I was, very pleasantly surprised that the technology is, when I talked to Zedong about it, he said, we are using 1 million hours of speech to train the system. And when we were doing research, 1 hour of speech was, we thought we died and went to heaven, and we didn't have the computing power at that time. Even in the 80s, when Jeff was there at CMU, we only had PDP-10s and maybe some VAXs and so on. And the emergence of cloud computing and the kind of computational power available today, we literally have 1 billion times more computing power today than we had in the 70s, basically. And that is what is making the difference. And I'm hoping we'll have another 1 billion in the next, 20, 30 years. That will give the younger generation like Yann and Yoshua and Jeff to kind of make further inventions. And you.
Well, Raj, I must say that the increasing computing power made this a huge difference. And I remember I got to CMU in '91. The first computer I got was the SunSpark station. And I noticed that. I said, God, it has 16 meg memory. I said, God, why do I need a 16 meg memory to do? I could do everything. And then I realized all those speech students in your lab have even more machines. I remember you used to have this AIX, IBM AIX machine no one wanted to use. Then you wanted me to use, but it's just too difficult to use. Anyway, so it's the computing power you are saying. So let me ask the next question to Yann. Yann, can you comment on the less than one-shot learning idea from Waterloo, and if that will have a big impact?
So I don't know this particular approach to less than one-shot learning. I mean, there's a number of different work on sort of, zero shot or, I mean, the vocabulary here is maybe a little exaggerated. It's the idea that it's connected to some of the stuff I talked about during my presentation, which is that you can train, for example, a speech recognition system on, a dozen languages, and then you will require essentially, very little data to get it to recognize a couple other languages that are in the same families as some of the ones you've already trained on. So you don't need to have, only a few minutes of data. Sometimes it doesn't even need to be labeled. You can use the phrase to describe it escapes me now, but it's basically the idea that you run your speech recognition system on unknown data. It's going to produce a guess as to what the sounds are that are in there, and then you sort of quantize those sounds. You kind of snap them to the sort of categories of sounds, whatever they are, and you use that as target to retrain. And that system will end up classifying the sounds in that language that you never heard before, and probably going to recognize sequences of phonemes that you didn't know before, but you're going to be able to translate that. I mean, to kind of transcribe. There is a very interesting piece of work from Guillaume Lample from Facebook from a year or two ago called Muse. This is a completely unsupervised translation system. So you train a self-supervised system to learn representations of words or phrases using this kind of completion idea of showing a piece of text, removing some words, and training the system to predict the words that are missing. In the process of doing so, the system learns representations of words or short phrases. And now a language basically is a cloud of points in the space of vectors representing those words or phrases. So you have language A is a cloud of point, language B is another cloud of point. And it turns out they're both human languages. They have similar properties. You can find a simple transformation that will make those two point clouds overlap, okay? You don't need any parallel text, and you get a translation system out of it without any parallel text. I find the fact that this works at all completely amazing, and it does. That's kind of zero-shot learning, if you want. That's an example.
I see. Yeah, there are certainly those buzzwords now. They are very exciting. Less than one shot, zero shot, and but the important things really get into the details. So I want to let our audience know that we're approaching the scheduled time, but we go slightly longer. Hopefully, get a couple of more questions, from our distinguished speakers. So I collected quite a few pre-submitted questions, and there are a couple of them actually asking for what do you think about the social impact of AI, and what are the most important things concern you with this fast development of AI? Any of you, if you would like to comment on that, maybe I start with Yoshua. And then
actually,
I go to
Raj raised his hand.
Or maybe I start with Raj, then we'll go to Yoshua. Raj.
So I was very gratified with what Yann said, that in their labs, they're able to do any language to any language translation with small amounts of data, not millions of hours in some sense. And this will have a profound impact on humanity. Basically, there are about 40%, 3 billion people who are either illiterate or semi-literate. They can't read any language, including their own native language. If they can read it, they can't understand it. If we can build these systems, you might call them guardian angel and intelligent assistants, if they can understand their master using this language understanding system, translate and execute their needs and desires, I think that'll have a profound impact, because essentially 35–40% of the population of the world is currently not benefiting from information technology or AI. And with this advance in AI and language technology, I think we are on the threshold it'll have a profound impact.
Yoshua.
Yes, here's my concern. We're building gradually more and more powerful tools. AI is just a tool. The problem is, as these tools become more and more powerful, they can be used in both positive ways and negative ways. And so how do we deal with the negative ways, right? That's the question. And as the tools become more powerful, the scale of the impact, of the negative impact, could be also more dangerous, whether it is things that threaten our global security, for example, with killer robots and things like that, or simply in the way that very powerful organizations, countries, large companies could scale up their power in ways that go against the public good. And so I think that we do need to think about these questions. We do need to potentially change the rules of the game, both inside each country and internationally, to make sure we can steer all of the agents, whether it is a country, whether it is a company or an individual, in a direction that prevents the misuse of those tools in ways that can harm the general public good.
Thank you, Yoshua. I have the next question. Hopefully we can also get this one for Jeff and for Yann. Did you foresee deep generative models, such as variational autoencoders, playing any role in your research? It's actually by a CMU alumni.
Maybe I could say something about that.
Great.
In, I think, 1994, Rich Zemmel wrote a thesis on variational autoencoders. And they weren't deep, and the deep variational autoencoders use an extra reparameterization trick. But basically, variational autoencoders have had a role in my research since 1994.
Yeah, maybe if I can say something about this. So I didn't have to really kind of talk about this in the talk today, but the type of models and things I'm working on at the moment are what I call regularized latent variable energy-based models, and variational autoencoders are a special instance of those types of models. GANs are another instance. Actually, GANs are more belong to another class of sort of generative model that are trained with contrastive methods, which both Jeff and Yoshua talked about a little bit, and I talked about a little bit. But I'm a firm believer at the moment in this idea of regularized latent variable models. So the basic thing there is that it's a way of dealing with letting a machine not predict one point, but predict a whole set or a distribution, but not going all the way to modeling a full distribution, because it's basically intractable for any interesting. We don't have a good probability distribution over images or video frames or things like that, right? We have it for text because we can do a softmax over words, but we don't have it for high-dimensional continuous representation. So for that, we need to probably use kind of weaker ways of modeling uncertainty, which I think should use things like energy-based models. And then to parameterize the set of possible predictions, you can have a latent variable that you can vary over a set or over a distribution that will make the output, the predicted value, vary over a manifold or a distribution. And the issue there is how you regularize this latent variable. This is a technical discussion, but that's really basically what I'm more or less solely kind of concentrating on at the moment.
Okay, thank you, Yann. And thanks, Jeff. So I'm going to ask the very last question, and hopefully it's a fun one. And any of you, feel free to have some short comments. And that I picked it from many tens of those questions submitted. Did you think that pursuit of conversational AI and the commercial chatbots will improve or degrade our ability to speak to other people? I'm concerned that talking to others in the future will become increasingly transactional. How can AI help us genuinely connect to other humans?
I want to answer this. Okay.
Okay.
So there is always, over the history of humanity, okay, without being grandiose, there's always been a fear that a new communication technology will completely disrupt the social fabric, right? So when books appeared, parents were telling their kids, like, don't read books. It's a complete waste of time. It will kind of mess with your mind. And in fact, it did. So, the printing press was invented. It totally did. People read, instead of having to, listen to the priest every Sunday morning, they could actually read, stuff by themselves. And that created a rift in Europe, in Christianity, right? There is a split between the Catholics and the Protestant, and it started religious wars and conflicts for 200 years. So just here's a technology, the printing press. Nobody today is going to say this was a bad technology, right? Nobody today is going to say that disseminating the writings of Luther and Calvin was necessarily a bad thing, okay? But it did cause 200 years of, death and torture and political rift, and basically caused the existence of colonization of North America, because there were basically religious people being persecuted. So yeah, technology has consequences. You cannot always control the bad consequences. Even good technology can have bad consequences, which is what Yoshua was talking about. And you can, every time a new technology appeared, it was not necessarily technology, but like a new way of communicating. Radio, helped fascism raised in Europe in the 1930s. Comic books and rock and roll were going to destroy the youth in the 1950s. Jazz was going to destroy the youth in the 1930s. And then the internet was going to destroy society. And now it's, social networks. None of this is true, okay? Absolutely none of this is true. All of those technologies transform society because they transform the way we communicate with each other. They change the, power structure and everything. They're mostly good, but as Yoshua said, we have to make sure we foresee the bad effects and we control for them. Very often they pop up before we realize they exist, and we have to take corrective measures. But I'm an optimist like Raj. I think technology is going to help, get people more informed and knowledgeable and connected, and language translation is going to erase cultural barriers. Get people to basically understand each other who would otherwise kill each other. So it's good.
So can I just get something straight? So I make sure I understand what you said. Do you think chatbots are going to cause less than 200 years of religious wars?
One thing you and I can hope for, Jeff, is that it will reduce the importance of religion.
Well, I do think there are some people start some AI religion, right? So it's there's always different views. Ross,
I think that guy. I think the guy who started an AI religion is now in jail.
Yoshua, Raj, you have any comments on this last question? Anything you would like to comment on?
No, I like Yann's and Jeff's comments. I agree with them completely. Basically, no matter what technology has been invented, there have been consequences of it, many good ones and some bad ones. It's up to the society to figure out how to effectively use technology. And in particular, I think AI, if there is an opportunity to build general purpose AI, I don't think we should be working on it. There are a lot of interesting problems in human-centered AI, which will help human beings, enhance the mental capabilities of human beings. And that's what we should be working on. There's not unlimited resources and unlimited funding. And even if you could do it, I don't think, my view is there's no such thing as general purpose AI. And I subscribe to Minsky's paradigm, namely, it's a large number of special purposes AI that together look like general purpose AI. He called it the Society of Minds in his book. I think that's what happens, basically. But Jeff is probably thought a lot more deeply about the our brain works and how it's interconnected. But I don't think there was some work done with respect to one of the neuroscientists said there is a small computer that only recognizes your mother's face, nothing else. And so there's so much specialization in the brain where every part of it is used for some special thing. And together it looks like it's a general purpose AI.
Thank you, Raj. Joshua, you want to have the final words?
I just want to say I agree with the general picture that Yann painted, except that I'm a little bit more concerned. And I suspect that it's not just going to be technical fixes that will be needed, but also changes in the very structure of our economic and political system in order to address the kind of danger of the powerful tools that we are and we will be bringing into the world. So I think more attention needs to be given to that as well.
Jeff, you have any more comments?
I want to sort of strongly emphasize what Yoshua has been saying about the need for things like regulation, the need for something like a Geneva Convention for autonomous weapons. I think people worry about the existential threat of AI, about the robots taking over. That's not the real problem, at least not for a very long time. The real problem is people like Putin using robots. That's what we need to worry about.
Yeah. Well, thank you very much, all the three distinguished speakers, and Yann, Joshua, Jeff, thank you so much for your wonderful lecture. And thanks to all our audience, we have several hundred people still hanging on there listening to us. We really appreciate your time. Thanks to the president and the dean of the school, for offering this wonderful opportunity for all of us to pay our respect to Raj. Raj, we love you, and stay home, stay strong, be safe and healthy. Whenever we can travel, we'll come back to see you to CMU.
Thank you, Harry. Thank you, Jeff. Thank you, Yann. Thank you, Joshua. So it's such a great pleasure, and thank you very much for taking the time.
Thank you very much, everyone.
Real pleasure.
Yeah.
Thank you, Harry.
Bye-bye.
Bye-bye.